Hey everyone, welcome back to Daily Dose of Space. Today, we're tackling a question that sounds simple, but turns out to be one of the hardest in all of science and engineering. Why haven't humans gone further into space? We landed on the moon more than 50 years ago. We have space stations, powerful rockets, and robotic probes leaving the solar system. So, why are humans still stuck in low Earth orbit? This isn't about conspiracy theories. And it's not about lack of ambition. It's about fundamental physical limits, many of which most people never hear about. Let's break down the real barriers to human space exploration. What stops us today, what might stop us forever, and what might be solvable. Distance. Space is much bigger than your brain thinks. The first and most underestimated problem is distance. On Earth, we're used to thinking in kilometers. In space, kilometers are meaningless. The moon is about 384,000 kilometers away. Mars, at its closest, is about 56 million kilometers away, and usually much farther. Even with our best current rockets, a trip to Mars takes 6 to 9 months. A round-trip mission takes 2 to 3 years. And that's just Mars, the closest planet we could reasonably visit. Beyond that, Jupiter is years away. Saturn is even farther. The nearest star system is 4.24 light-years away. At current propulsion speeds, reaching another star would take tens of thousands of years. Distance alone already makes human exploration exponentially harder than robotic missions. Propulsion. We've hit a practical wall. Rockets today still work on the same basic principle as in the 1960s. Throw mass backward to move forward. Chemical rockets are powerful, but horribly inefficient. To give a sense of scale, over 90% of a rocket's launch mass is fuel. Every extra kilogram of payload requires exponentially more fuel. This creates a brutal trade-off. More speed, more fuel. More fuel, heavier rocket. Heavier rocket, even more fuel. This is known as the rocket equation, and it's unforgiving. Advanced propulsion. Ideas exist. Nuclear thermal rockets, nuclear electric propulsion, ion drives, solar sails. But here's the problem. Some are too weak for humans. Some are politically or legally restricted. Some are still theoretical. None solve interstellar travel. There is no known propulsion technology that allows fast, crewed travel beyond the inner solar system. Microgravity. How space slowly changes the human body. One of the least visible but most serious challenges of spaceflight is microgravity. On Earth, gravity constantly pulls on our bodies, shaping how our bones grow, how our muscles stay strong, and how our organs function. The moment that force disappears, the human body begins to change in ways that are surprisingly fast and, in some cases, permanent. In orbit, astronauts experience bone loss at a rate similar to severe osteoporosis, but happening much faster. Weight-bearing bones, especially in the hips and legs, begin to lose density because the body no longer needs them to support its own weight. Muscles weaken for the same reason, even with strict daily exercise routines. The heart, which normally works against gravity to pump blood upward, gradually adapts to the easier conditions, changing its shape and strength. Vision problems have also become a growing concern. Many astronauts return from long missions with lasting changes to their eyesight, likely caused by fluid shifts in the body that increase pressure inside the skull. The immune system becomes less effective, and recovery back on Earth can take months or even years. What makes this especially problematic is that a mission to Mars would expose astronauts to microgravity for far longer than any mission we've completed so far. Even if partial gravity on Mars helps slightly, we still don't know whether the human body can handle multiple years away from Earth without accumulating serious, irreversible damage. Life support. Surviving means zero room for error. On Earth, survival systems are invisible. Air surrounds us, water flows freely, and food can be replaced easily. In space, none of that exists. Every breath, every sip of water, and every degree of temperature control depends on machines working flawlessly. The International Space Station survives thanks to constant resupply missions and immediate access to Earth in case of emergencies. Even so, failures still happen, and crews rely on redundancy and rapid ground support to solve problems. A deep space mission would have none of those advantages. There would be no resupply, no rescue, and no quick return home. Life support systems on a Mars or deep space mission would need to recycle air and water almost perfectly for years at a time. Any contamination, leak, or mechanical failure could escalate quickly into a life-threatening situation. Designing systems that can operate autonomously for that long, without maintenance from Earth, is one of the hardest engineering challenges in spaceflight. So far, we've never tested a closed life support system for humans beyond low Earth orbit for extended durations. Until we do, long-distance human missions remain an enormous risk. Isolation and psychology, the mind under pressure. Space exploration doesn't just challenge the body, it challenges the human mind in ways we're still trying to understand. Astronauts on long missions face isolation unlike anything experienced on Earth. Communication delays increase with distance, meaning conversations with Earth lose their immediacy. At Mars distances, messages can take over 20 minutes to arrive one way. This creates a sense of separation that no training simulation can fully replicate. Crews would live in confined spaces for years, surrounded by the constant awareness that a single mistake or system failure could be fatal. There would be no fresh environment, no privacy, and no true escape from the mission. Studies from Antarctic research stations, submarines, and simulated Mars habitats show that long-term isolation can lead to mood changes, cognitive decline, sleep disruption, and interpersonal conflict. Even small tensions can grow over time when there is no way to step away from the situation. The psychological demands of deep space missions may ultimately be just as limiting as the physical ones, especially when missions stretch into years rather than months. Energy, powering life far from the sun. Every system that keeps astronauts alive depends on energy. Life support, communications, heating, cooling, and scientific instruments all require constant power. Near Earth, solar panels work well, but as spacecraft travel farther from the sun, solar energy becomes weaker and less reliable. Nuclear power offers a solution, providing long-lasting and consistent energy, but it comes with political, legal, and safety challenges. Launching nuclear material from Earth requires extreme precautions, and international agreements limit how these systems can be used. For human missions, power systems must operate continuously for years without failure. Even a short interruption could have serious consequences. Designing power sources that are both safe and durable enough for deep space remains one of the key unresolved challenges of human exploration. The cost of going far, economics and priorities. Human spaceflight is not just technically difficult, it is extraordinarily expensive. Sending people beyond Earth orbit requires massive launch systems, complex spacecraft, life support infrastructure, and years of planning and testing. A single human mission to Mars is estimated to cost hundreds of billions of dollars. Robotic missions, by comparison, are far cheaper and far less risky. Robots don't need air, food, or protection from psychological stress. They can operate in extreme environments for decades and continue returning valuable data long after a human crew would have had to leave. This economic reality shapes decisions at every level. Governments and space agencies must constantly weigh the scientific value of human missions against their cost, especially when robotic alternatives can achieve many of the same goals more efficiently. Why robots are our best explorers for now. When we look at how far we've reached into space, a clear pattern emerges. The most distant objects ever explored were not visited by humans, but by machines. Probes like Voyager and New Horizons travel where humans simply cannot, enduring radiation, cold, and isolation without complaint. Robots are immune to many of the constraints that limit human explorers. They don't age, they don't suffer from bone loss, and they don't need to return home. This makes them ideal for exploring distant planets, moons, and even interstellar space. For the foreseeable future, robotic missions will remain humanity's primary way of studying the far reaches of the universe. What could realistically change in the future? There are ideas that could reduce some of these limits. Artificial gravity habitats might help preserve human health. Better radiation shielding could lower long-term cancer risks. Advanced propulsion systems could shorten travel times. However, most of these technologies are still experimental, and none eliminate all the fundamental challenges at once. Even under optimistic assumptions, Mars may represent the practical limit of human exploration using known physics and technology. Beyond that, the risks and costs rise dramatically, while the benefits become harder to justify. Interstellar travel, as fascinating as it is, remains firmly in the realm of theory rather than realistic planning.